Welcome to this presentation about reservoir optimization, part 1 of the RTC Tools training. My name is Bernhard Becker. I work at Deltares in the Netherlands, and I'm also external lecturer at the RWTH Aachen University in Germany. First, a few words about Deltares. Deltares is an independent research institute for water and subsurface. The hydraulic laboratory of the Netherlands is hosted at Deltares. Here on the right side, little impression on that. We have the Delta flume. Maybe you have heard about that. That's the flume that generates the highest artificial waves in the world. But also Deltares is known for software for hydrology, hydraulics and geotechnical engineering. For example, Delft 3D, SOBIC, RTC Tools, the software we will work with today, IMOD for groundwater modeling, WFlow, hydrological modeling. And also you might know about the forecasting platform software, DelftFuse for operational water management. About 800, a bit more, employees from 39 nationalities work at Deltares, and we have main offices in Delft and Utrecht in the Netherlands. Deltares in the Netherlands. The Netherlands is not a reservoir country, I would say. It's a flat, low-lying country at the coast here in this area in Europe. But this does not mean that we don't deal with reservoirs. Here you see a map of operational forecasting systems in the world that are built with DelftFuse. And here on the legend, you can see that we have drought forecasting, but also flood forecasting and reservoir management, hydropower. These are tasks that we address with DelftFuse. And within DelftFuse systems, sometimes there is an RTC Tools optimization model, and that's the topic of today. We start with a lecture about reservoir operation in general. This is part 1 now. We'll discuss feedback control, model predictive control, and added value of optimization for reservoir operations. Second lecture is about mathematical optimization. We will discuss global and local optima, linear problems, nonlinear problems, Pareto optimization, and lexicographic goal programming. And this will then flow into a part 3, kind of demo or hands-on, if you like, kind of exercise. You have to install RTC Tools beforehand, and then we work with a simple reservoir model. The software is RTC Tools. RTC is an abbreviation for real-time control, and we call this a toolbox. It's an open source toolbox for control and optimization of water systems made by Deltares. And with toolbox, I mean it's more a kind of MATLAB-like working rather than a modeling suite with a user interface. So it demands a bit more from the modeler on the one hand, but on the other hand it gives also much more flexibility to model the system that you are working with. Learning goals: basic understanding of reservoir operation, the two operational concepts, feedback control and model predictive control, and the added value of the optimization mentioned before. I want to provide a basic understanding of mathematical optimization, only focused on what we need for the model. And also a third learning goal is to introduce this open source software for optimization of water systems. I already mentioned it requires some code configuration. In our case it's Python, and then you make first experience with an optimization model. What do you get out of it, and what can you do with it? So, control of water systems. Why are we dealing with this topic? The thing is that there are a lot of human interactions on water systems to get control on the water cycle, and we use we have hydraulic structures that we operate. Here some images about hydraulic structures, some examples. Here floodgate, coastal engineering, then this is a reservoir, classical type I would say, the Edertalsperre Dam in Germany. Here from the Netherlands, it's a pump station in Kinderdijk, and this is a Weir in Belgium. Reservoirs, yeah, we can say that they consist of multiple hydraulic structures. It's the dam itself, but it has a spillway here, in this case, with these arcs here, a powerhouse and a bottom outlet. And today we will focus on reservoirs. Elements of a dam or a reservoir, if you like. Here, this is the dam, the main building, and it dams up a river, and then we get a reservoir lake here. On the other sides, the downstream sides, that's the tailrace or tailwater, and the dam has a spillway for flood situations. If much water comes, it must be able to pass water across the dam such that the dam does not fail or is damaged. Under normal conditions, usually we use the powerhouse to generate energy, so water flows from upstream to downstream through the turbines. And some dams have a bottom outlet which allows to guide water through the dam without passing turbines. Here I found this wonderful picture, and here it's in operations, the bottom outlet. And very important for energy production is the head difference between the water level in the reservoir lake and the tailwater level, and in combination with the flow through the turbine, this determines how much power we can get out of this situation. And multi-purpose dams are usually operated with different water usage or use functions in mind. Hydropower production, for example, its advantages if the water level is as high as possible, and then we would like to release water through the turbines. But the opposite is the case for flood protection. There it's good if the reservoir is as empty as possible, because then we have more flood storage volume. In case of a flood, we can catch more water and prevent damage downstream. Other use functions: water supply for agriculture, industry and drinking water, public supply, environmental flow, minimum flow, fish protection. Minimum flow can also address cargo ship navigations. Recreation, boating and swimming, maybe in the summer more important than in the winter. Water quality issues have to be considered usually. Evaporation losses, yeah, that's a bit tricky because we cannot really control that, but yeah, if the water level is low and the surface area is small, then we lose less by evaporation. And some dams also address groundwater recharge. And we have already learned there are some conflicting usages: flood protection, hydropower, but also hydropower usually conflicts with fish safety, and also water supply for water use might conflict with recreation, and there are certainly some others, and usually operators have priorities, what is more important or the most important in comparison to other use functions. And this is something that RTC Tools can help to address or even to solve. To give an example what can make sense in reservoir operations to address these different goals. Here you see the flow in an unregulated Tovdal River in Norway. I took this from a ICOL Congress proceedings. Here you see this is upstream of the reservoir, the flow over time, and there's a little flood peak here, or little, it's quite significant here, 200 and 1200 cubic meter per second. And what the operators have done is they have released the water in the reservoir beforehand, as you can see here. So this is the water level, and then this pre-release reduces the the discharge downstream of the reservoir, and this is the purpose is to prevent floods. Yeah, we have different control methods to make this happen. The first and more simple one is feedback control. So feedback control means that we base our actions, decisions on the current observations. Control actions must be defined beforehand. We have flow charts or decision trees. Here's an example. And then there are operating rules. For example, switch a PID controller with a set point or switch to on-off mode, release water or not. That would be a very simple case. So here this cartoon illustrates that we look at the current water level, for example, and then we know what to do. Advantage is that it's very easy to implement in practice, but also in modeling in software. It's very straightforward, easy to understand, but it's less easy to anticipate on future events like we have seen before. And also the operating rules must cover all possible situations. And this means also that the set of operating rules we have, for example this flow chart here, will never match perfectly. So we more or less never have optimal control. And it's not the best that we can get out of the system. Typical feedback control mechanism is the pool-based rule curves concept for reservoirs. Here you see over the month in a year, the month in a hydrological year, here starting in November, and the vertical axis has the reservoir volume, and we look at a certain month. Here, for example, in January, flood season, if the reservoir is filled quite well, 200 here for example, then this color indicates the release for that particular time in a year. So here it's 40 cubic meter per second. This is all in German because this is about a German dam. If there's less water in the reservoir, then we release less, and here the white space, that's kind of a dynamic range where the operators can decide by themselves between 11 or 6 what they want to release. And if the reservoir is filled with water up to the maximum volume, then the discharge is even higher. In the summer, it's quite different. We have for the same volume, 200 for example, we have a different release. So here it's only 25 for example for the 240, and the minimum flow here 5 and 6, this curve goes a bit higher, so we start earlier to go down to the minimum flow because there's less water flowing in to the reservoir in the summer. So here's a typical clear advice on how to operate. If then else, if we have the day in the year and a certain volume, then this table or this graph gives us the reservoir release. Second control method, and this is what RTC Tools where RTC Tools comes in, it's model predictive control. The functional principle is quite different. We asked optimization model, find the optimal control pattern for the current situation and meet all goals as good as possible. We work with goals or targets instead of condition and rules. So it's not if then else, but goals. For example, meet the load balance, maintain a maximum water level here or there, and maintain a minimum river discharge. And then the model finds a control pattern with the help of an optimization algorithm and a model that computes the system answer on a certain control pattern. And here this cartoon is much more complex, so we feed optimization algorithm with targets and constraints, a schematization of the water system, and a scenario, for example, is the forecast for the next 2 weeks, or a seasonal forecast for the next 2 or 3 months. And then this model gives a time series, and this is what the operator can choose to implement as reservoir operation. Advantage is it can anticipate on future events as long as they are part of the scenario, because we don't look at only one time step but the whole forecasting range. We work with targets instead of rules, so we rather say what we want and not what should happen, and this can result in optimal management. Drawback is that we need mathematical optimization techniques, and they come with special requirements for water system model schematization and model setup, so it's more complicated. And what we get is a period of record solution, so a solution that fits on this particular scenario, and this will not work for all other situations, so we have to use this model or this modeling system during operations. We cannot translate that into a if-then-else rules book or a table or a graph that we have seen in the previous slides. An example for an application, the Salto Grande Reservoir in Uruguay. Salto Grande Dam is quite large. Its dams up the Rio Uruguay, has a catchment area of 240,000 square kilometers. This reservoir or dam is used for flood control and hydropower, and the mean annual inflow is 4,700 cubic meter per second. What we have done so far in a study is we used RTC Tools optimization with different forecast length, 14 days or 7 days, and compared that with the historical operations. What we can see here in the results, first these two colors here, different forecast length gives a different result because the model can look further into the future. And what we also see is that we can maintain higher water levels with RTC Tools, with a model predictive control compared to the historical scenario, here the gray lines. And also anticipating behavior, a pre-release of water. You see here the reservoir stage over time. So the reservoir is drawn down to anticipate on a flood wave that is coming in. Also interesting is the spillway discharge. Again here, 2 model runs for different forecasting periods. In total we spill less compared to the historical operations, and the longer the forecasting period, the smaller is the spilled amount of water. And this is interesting because spill is always a bit dangerous, spillway usage, but also it's kind of waste of water, because we would rather like to guide that water through the turbines and produce energy with it. And this is what the next table says. Here the historical energy production was 17,100 gigawatt hours. With the 7-day forecast it increases a bit to 1850. 14-day forecast, we have again a smaller number, but it's still higher than the historical value, 17.940. Compared to the historical operations, an increased power sales here of 114 or 100.8 million euros. This is quite something, I would say. And most interesting maybe the maximum discharge. Instead of 30,000 we have 23 or 22,000, which means less floods. The flood is not as severe as in the historical case. And then release via spillway, so also smaller numbers, and here the 40-day forecast performs best. So this means with an RTC Tools model predictive control approach, higher water level in the reservoir, less spill, larger energy production, and higher flood security level. But we must also mention here we have used kind of perfect forecasts, so we used the historical data for this optimization and we got these nice results, but in the real world of course we don't know exactly what will happen in the future, so there will be also some uncertainty involved. So this will not be possible to realize these figures in practice because the future is uncertain. Another application example is strategic planning and rule curves. optimization can be used for to develop rule curves, which means over the month and a year a minimum water level that the reservoir should have. So the question is, what would be the best operational scheme? What would have been the best operational scheme for a certain year under the given goals? And we have done that for I think it's 87 years here in this example, and then with some simple statistical analysis, min, max and quantiles, we can derive minimum and maximum water levels, or volumes here in this case. So this is water level, minimum water level or maximum water level, and this is the operational range that should be applied for reservoir operations, and accounts for flood filling season. So don't go higher than this, because then here we need flood storage, and in the summer here we need water in the reservoir to bridge towards the next filling season. So that was the first part of the presentation. This is a pre-recorded lecture, so if you have any questions, you can address me via the email. That's on the first slide, via email address, and here's some generic information about deltars. Thank you very much.